Hey, what's going on, YouTube? What's up? I see we already have a few regulars in the chat. How are you all? It's good to see you. Yeah, today's another discussion session. This is an office hours. I don't have anything specific planned. I have a few ideas in mind of things that we could work on and take a look at today. But I'm here for you all. If anybody has any requests, any questions, especially about the content that we've done so far, I would love to help out. If anybody has any questions or anything, what's up? Let's just confirm. I do believe that I'm live and my microphone is working and everything. Good. Okay, so first things first, I do want to draw attention to my brand new video announcing season 2. So we could talk a little bit about the topics I have in mind and get some thoughts, get some feedback, requests. Like generally, I see this time as a moment to check in with you all and understand, if we're moving too fast, too slowly, what types of topics do you all want to cover, things like that. As well as, hang out a bit, but if you want to just hang out and chat, I think that's what the weekday live streams are for. This stream, I want to actually be a working session and actually work through some math, and be somewhat focused. What's up, Unix Teletype, Quitch Math, Anchor? What's the point of learning math if AI will solve every unsolved problem and create new maths? It's just going to be good for your brain. Like, why go to the gym if AI can already do it? Like, I don't know. You still need to feed yourself mentally and physically, I think. What's up, Webmaster? How's it going? Okay, so season 2, y'all, please do check out this new video if you haven't already. I think it's good. I put a lot of work into it. That thumbnail is now going to be the new template thumbnail for the next 10 episodes or so. So I want to give a sneak peek. I think that my first episode is going to be about mental math and arithmetic. Like arithmetic practice. But really, more so mental math and deliberate practice. Oh my goodness. Maybe I'll talk a bit about what deliberate practice means to me, in a little bit more detail, and try to compare with scales in classical guitar, which I have a lot of experience with. What are some equivalent things that people do that are like fundamental skills, like a fundamental foundational skill that you deliberately practice and continue practicing forever? Things like serving in tennis, like practicing your serves, or chopping an onion. Chopping onions, that's like a really fundamental skill that you want to keep practicing and getting really, really good at. Katas in martial arts. Also katas in coding. Hey, what's up? Syllabus with Vicky. Hello, sir. I am from India. I want to master mathematics, but I am struggling with basic math. What do I do? Have you found this book yet? I have an affiliate link in my video descriptions, so you can get a paper copy that way, and you can also find PDF copies online. So I'd say get this book and work some exercises. Like, what kind of struggling are you having? This session is about this book and about my video series on based on this book. So I'm not going to work random other problems, but please let me know what you're struggling with, and also subscribe to my second channel. At jcpractices math. Here I will help you with any kind of math. Yeah. And I can take more off-topic questions and things. All right, so I think that we could be cool. You want to master this book's concept. So how's it going so far? We've done sections 1.1, 1.2, 1.3. I did a section on logic, and then I did a section on proof by induction. If you have a specific, what I'd say generally, like how to practice math, dude, exercises. You need to be working a lot of exercises. So how are the exercises going for you? If you're working through this book, which ones have you tried? Which ones are you getting stuck on? I'd be happy to help if there's any specific exercises that people want help with. That's what this session is really, really built for. What's up, Webmaster? What's up, Rafael Lopo? How are y'all? Okay. So my next video is literally going to be about practicing addition and multiplication in more detail than I've done before. Maybe I've done this topic too many times already. Maybe it's time to just keep moving on. If anybody has an opinion there, it may not be my next video, but like, I feel like there's still more I want to say about it. I am doing things like really logging, like really logging and tracking my progress over time on these exercises. For example, on reverse odds, I practice this one every day. Let me get a let me pull up my tracker. I'm tracking this in a spreadsheet, and I want to share this with people soon. My reverse odds exercise, I think, is my A3 column. I've gone from 12 to 12.1, 12.5, 13, 13.4. Like, I am getting better at this exercise. 13.4, 13.7, 14.1, 14.5. Like, look at this. I'm getting better and better over time. Like, it feels really great to be seeing tangibly that I am making progress on this hard exercise. 14.2, 13, unfortunately. 14.4. 14.4, 13.1, and then 15.1. So this is getting better. I'm getting better at this exercise. I'm going to call this a score. How to buy this book? Get the book. Yeah, just get it. dude, get the book one way or another. My affiliate link for the book is right here. If you want to buy it, it helps the channel. It really, really does. But you can find it. You can also find it. Yeah. So we can see, I mean, just clearly, I am improving at this exercise, which is so sick. I don't think that this is currently properly spacing out based on dates, but like, check this out, dude. Check this out. Here's a sneak peek. Oh my god, wait. I have to hold this button. What is the exercise you're doing every day? Let me show you. If nobody has a question, I'll just work it for a bit. But I can see, because I've been building a little Google spreadsheet that I want to share with you all. Look at this. It's getting better. I'm getting better over time. Like, how cool is that? How cool is that to see? Okay, so the exercise, if nobody has any specific questions, here, let me pin a message. Let me pin a message. Ask questions from the book and series. Yeah, I mean, internationally it might be expensive. In the US, it's a cheap book, actually. It's only $30, whereas a lot of textbooks in the US are 100 or more. So, I don't know, I can't solve these things. What will be the main topic of season 2? Let me answer that first. If you haven't seen it, dude, Cyber Potato, what? Come on, man. You haven't seen my video yet announcing season 2? I made a whole video about this. It's in there. One of the bookmarks, part 4, season 2 syllabus and changes. This is what I'm currently thinking. That the main topics, you commented but you didn't watch. You forgot to watch even though you commented. Come on, bro. Now I know not to believe in your comments anymore. You said W and you didn't even mean it. These are the topics that I'm imagining in season 2. Yeah, you can definitely find. It's a soft cover. That's why it's only $30. Yeah, I'm very happy that this book is affordable. It's actually quite affordable for a Springer book. Like, Springer books can be more, twice as expensive. No worries, dude. You're bad. I know you're gonna watch it later. Please do watch it though, Cyber Potato. More than my other recent videos, this one is meant for everybody. This one is not, like, I'm not actually teaching math in this one. It's just actually a vibey video. It's just talking. It's just a talking head video like that first one. Yeah, watch it. If you want to watch it right now and come back and let me know what you thought, you could, but that's up to you. So these are the topics from the main book that I'm imagining, and then all the question marks I think are topics, supplemental related topics, related videos that are going to be topics that I am bringing from my experience as a math major, as somebody interested in math as an art form, math as a hobby. This book is still designed to prepare somebody for calculus. And so it doesn't get as deep into the math as a hobby, math as an art form type of math as I would like. So I'm bringing What's up, Patricia? Thank you. Yeah, yeah, we could do a pen spinning tutorial sometime. The videos are there so you can do it at your own pace. Yes. Yeah, absolutely. Um, do you have some advice for onboarding now? Just found your channel and probably need to work through season one quickly. No, dude, please take your time. Those videos are not going anywhere. They're really not going anywhere. Uh, you know, most importantly, my videos are expecting you to be working exercises and actually working through the book. I'm trying, and this is a question to you all. Do you like this idea of like what does like a YouTube lecture series look like? Like what if we ran an actual course on YouTube, like an actual series where I'm expecting you to read the same book with me and do homework. Like, what would that look like? I don't feel like I've seen that before. Okay, so we will be adding some new sections. I said 1.3. That's a lie. Dang. And it's too late now. It's too late to change it. That's a lie. This one is section 1.4 because 1.1 was integers, 1.2 was addition, 1.3 was multiplication. Oh well. Oh well. Please start series. Yeah? Go watch them. I'm treating the lecture series as a course. That's fantastic. I'm really happy to hear that, Patricia. It's good to see you, Patricia. Thank you for joining us. Have you seen the new video yet? I think it's good. I think it's good. Like I tried to put effort into it and make it a good video. Wherever the heck it is. Thumbnail. Here's season 2. Here's the template, the new thumbnail style for season 2. All of the videos, 10 videos in a row, are going to have very similar thumbnails. Okay, and anyways, somebody asked what topics I'll be doing. Those are some of them. I could give a sneak peek. The first episode, I'm thinking practice, like practicing addition, practicing multiplication, just getting comfortable with numbers. There are a lot of comments I'm getting from people who say that they want to learn proofs, but just they struggle with numbers and they like have anxiety and they hate calculation, that they're not good at calculation. I want to offer this idea that I think that you only need to learn a couple of exercises. And for addition, I have two favorites. One is Fibonacci numbers, and this is a classic that a lot of people do. I also practice this one and I track it. So all you need to remember is 1 and 1, or 0 and 1. 1, 1, what is 1 plus 1? 2. What is 2 plus 1? 3. 3 plus 2? 5. So you continue there, right? Add the last two numbers. Try to do this and try to practice this in a way that you can do them mentally, or at least without like the little scratch paper, column addition way. You're going to get better and better at thinking more mathematically about addition. What is nice about Fibonacci is that it's so easy to remember and get started with, and there are beautiful math patterns that you can prove. So it can be like a really good example of a sequence to learn about, because we can keep coming back to it and seeing deeper facts about numbers with it. But right now, that's not my favorite addition practice. My favorite right now is this sequence, reverse odd sums. And this is episode 8, if you want to see more details about it. Let me know if that person who asked is still here. Somebody asked what exercise, but that was a little while ago. That's excellent. If you're pausing and taking notes, that's the way to do it. That's actually how I want people to watch my videos. And it's probably not good for me as a YouTuber. Like my video style is probably not very good for the YouTube algorithm, because it's like it asks you to pause and work exercises, and maybe you stop watching the video, so like maybe the average view duration isn't as long as a regular video, as what YouTube is expecting, because I want you to pause and actually work examples and stop the video if you need to come back to it later, which is fine. Like the purpose is to be learning and doing a real, math lecture series. All right, reverse odd sums. What I like about this one is that it stays in the 2-digit numbers for a long time. Oh wait. Yeah. It's a little harder to explain, but I tried to explain it pretty well in episode 8. And I can explain it in a moment here. Okay, so there's the beginning of the sequence. So notice that in roughly this, I went quite a bit further than the Fibonacci numbers, but Fibonacci very quickly gets to 3-digit, 4-digit numbers. And typically in the real world, you don't have to add 4-digit numbers very often, especially not mentally. This practice really keeps you in the 2 and 3-digit numbers for a long, long time, and you get a lot of really good practice, especially like sub-vocalization. Sub-vocalization practice is important for getting better at mental arithmetic. I don't know if I want to explain the pattern here, because that might spoil it for some people. In episode 8, I constructed episode 8 in a way to try to make it a puzzle and let you pause the video and try to figure out the pattern yourself. So I think I'm going to leave it at that. I don't want to give it away right now unless people really want it. I don't know. I guess I could. Hope that makes sense. So anyways, this is the one that I'm practicing almost every single day. And in my next video, I'll talk about how, and I'll share more about how I am tracking this in, I don't really analyze the Google Sheet, but I am mostly tracking it in a paper notebook And it's just so motivating to see that a hard exercise, even with a hard exercise, I'm getting a little bit faster. I set a 5-minute timer. 5 minutes. And then I practice it for 5 minutes straight and see how far I go. You'll show the exercise you're doing every day in the next video. Yes, I will. I will talk about it and explain it quicker, like much more succinctly, in the next video. But if you want to see it right now, episode 8 is the one. It's the whole focus of episode 8. So season 1, episode 8. Go check out that video if you want to see it. I don't want to spoil it because it is designed to be kind of a puzzle. Yeah, I think you'll like it. It's really good. It's really, really good. So that's what I practice for addition, but I also practice a couple of things for multiplication. My favorite is the Collatz conjecture. Specifically, Collatz 27. Collatz 27 is awesome. I look forward to the day someday. I don't think I'll ever be able to, but also a 5-minute timer. How far can you get in Collatz 27? Let me get the numbers for this one too, just for funsies. Collatz 27 is M2, and I've started putting these into, tracking them in a Google Sheet. So, dang, really? Wait, is that a typo? Okay, I think I made a mistake early on that one. I went 7, 37, 26, 33, 38. This one I don't mind spoiling a little bit or something, or just telling you about and explaining the pattern. Let's see. Let's delete this, and I'm going to call this for multiplication practice. I do Collatz 27. Collatz 27, this is episode 5. I teach the Collatz conjecture. And I teach it partly as an introduction to functions, and I use it to teach kids and introduce functions to kids. But where am I going with this? It's really simple. Odd numbers, you triple plus 1. Even numbers, you divide by 2. Okay. Odd numbers, triple plus 1. Even numbers, divide by 2. 27. So if you start with 27, this is the first number that takes a long time, just surprisingly long, until it bounces up and down, and then it finally finishes. So I would be so impressed if somebody could finish this in 5 minutes. Let's do 1 minute. Let's do a 1 minute Collatz 27. Hey Siri, set a timer for 1 minute. Okay, so 27. Wait, that's not right. That. It's been a little bit. That's not right. That's broken. What did I do wrong? Triple 50, 141, 142. Oh, okay. There it is. Well, I tried my best. I made a mistake in there. Okay, so triple 27, triple plus 1. How did I think of this one? I thought of it as 30 times 3 minus 3 times 3. 30 times 3 is easy. It's 90. 90 minus 9 plus 1. That's how I got that one. Taking half of numbers is easier. That one isn't tricky. Triple plus 1, 123 plus 1, not too tricky there. 62, half of that. That one's not tricky. 94, 47. That takes a moment to think about, I think, until you're getting better and better at your halving. You can think half of 80 is 40. 94 is 80 plus 14. So half of 80 is 40, half of 100 is 50, so it should be between 40 and 50. And it's definitely not 42. The other number that doubles and has a 4 as the ones place is a 7. 2 times 7 is 14. Because of that ones place, we either need the last digit to be 1 or 7. Okay, so half of that is there. This one I thought of as 150 minus 9. Because 47 is 3 away from 50. Half of that, not hard. But yeah, I stumbled for a moment on 47 to 142 here. Your subscriber growth was crazy, though. I forgot your initial sub count for a second. Yeah, dude. Yeah, you've been here for a while, Cyber Potato. Did you already watch that whole season 2 episode? Yeah, you've been here before the blow up. I was at 1.7 thousand. 1.7 for a while. And then, I mean, I was consistently growing, though. In this channel reboot, I was really consistently growing, which was very encouraging to me. It was already looking quite good. But yeah, what Cyber Potato's talking about is when I posted that first video, I had 1,700 subscribers. Then suddenly the video popped. I had 2048. Then I had 4096 just the next day. And then like the day after that, the day after that, I doubled again. And then a couple of days, 3 days after that, I doubled again. So in 6 days, I grew 8 times in 6 days. And then it's been consistent growth. When I filmed this video 2 days ago, it was 3917. Right now, we're already, since I filmed this 2 days ago, yeah, dude, see, I'm telling you, this is what I'm more encouraged by. It's not like it's slowing down or tapering or anything. I've already gained 1,000 subscribers since filming this video that you just watched 2 days ago. Like, that's insane to me. I've already almost gained as many subscribers in 2 days than I started with that I had before that first crazy video. So, sorry, I don't mean to be turning this into non-math stuff. That's not math. Let's get back to the discussion. So, my point is that this is an excellent multiplication practice exercise. I really, really think that if you get good at mentally tripling and doubling numbers, you can get a lot of freaking you can build a lot of other multiplications, like multiplying something by 6. I triple it and then I double it, right? Multiplying by 4, I double, double. Rarely need to multiply something by 9, but sometimes I do. I mean, if you get good at tripling, maybe you see it that way. Or maybe you see it as times 10 minus 1 or something. Well, times 10 minus n or something. Like, what are you doing? What is happening? Is Luna sitting on another? Oh my god, what is happening right now? Okay, I'm back. Yeah, it's been wild, man. I don't know, multiplying something by 7. I'd multiply by 5 and then I distribute 7 as 5 and 2. Multiplying something by 5. Well, you can get good at multiplying by 5, or you could get it good at multiplying by 10 and then dividing by 2. Like, if you're good at dividing by 2, you're also going to get better and better at multiplying by 2. Taking half and doubling is kind of, they're kind of the same math fact or the same thinking pattern. So if you're really good at taking half of numbers, you can also multiply by 5 pretty quickly. So these types of tricks, I don't think I learned them when I was young. Yeah. So I feel like my multiplication is getting faster just by practicing 2s and 3s. If you get really good at 2s and 3s, you're going to be getting better at all the other ones as well. And of course, at some point on these, like, there's nothing wrong if you do want to be practicing the algorithm approach. You can do that too. You know, it's your time, it's your hobby, it's your practice. If you want to focus on just getting really good, really quick at doing the table algorithms, that's awesome too. My wife beats me all the time at the Fibonacci numbers. She's faster than me for sure at addition. And she just uses just a straight, like, little table approach. I'm just like, how do you write that fast? How do you write so quickly? But yeah, she consistently beats me by like a few numbers or so. And we're both tracking our numbers because we're nerds. We're such nerds. Yeah. All right. Hope that answers the question a bit about the exercises that I'm practicing. And I'll get in more details about this in the next video. If nobody has any specific questions about the course or the section so far or anything, I think, Patricia, if you're still in the chat, if you're still observing, why don't we talk about factoring now? Because I know Patricia was craving some factoring practice. Hmm. Okay. If not, that's okay too. Ah, you're here. Okay. Want to do factoring, or do you have any questions about the sections so far? I know, yeah, you've been wanting to talk about a bit about polynomials and factoring. Oh, my pen is broken. What happened here? Yeah, factoring. Okay, cool. So I think factoring, we want to be practicing factoring of quadratics first. We really want to be practicing this and getting good at this before we start thinking about higher degree polynomials. You don't have to factor a higher degree polynomial as often. Um, Quadratics are the best ones to start with. What is a quadratic polynomial or a quadratic form mean? Again, a quadratic is a function in one variable of this form. There are three coefficients. There's an x term. There's an x squared term, the quadratic term, the linear term, and the constant term. So there are three terms in a quadratic. Now, the simplest, this is the general case. Also, we should, if it's truly a quadratic, the leading coefficient should not be 0. Because if the leading coefficient is 0, then we just have, bx plus c. This is not a quadratic. An x squared term doesn't affect this polynomial. Okay, so let's get some examples. Let's build some of our own examples. Again, if I have ABC, what happens if, let's pick our favorite numbers. What are your favorite numbers? Mine are probably 1, 2, 3. They're simple. X squared plus 2x plus 3. Here's one example. Maybe Fibonacci numbers, 1, 1, and 2. Maybe prime numbers, 2x squared plus 3x plus 5. Maybe powers of 2, x squared, 2x, and 4. Let's keep making up some others. So here are some examples of quadratics. And we could plot them. We can do other things that we will learn more about later. But the simplest one is x squared. And we do want to at least know the shape of this one. X squared, as a rule, is fairly straightforward. X and x squared. We're just going to square numbers. And this is something that we want to get good at, knowing the square numbers, the perfect squares. 1, 2, 4, 9, 16. But also, when we square negative numbers, they also have the same values. Because negative 4 times negative 4 is positive 16, for example. Hey, what's up, hell yeah? Yeah, it's been a while. How have you been? Everything has changed. Yeah, I've rebranded this channel. I now have a second channel where I do my regular live streams. If you haven't subscribed to that one already, go check that out. This channel is now completely focused on this, on my video series, and it's blown up like crazy. It's insane. Okay, so knowing that, we can plot some points. They're going to look something, if you got some graph paper or something, it's going to look something like this. And if I draw a smooth line between them, we get this shape. I think that we call the graph itself a parabola. 1 squared is 1. Oh, what am I doing? Yes, thank you. I don't know what I was... Yeah, I got confused. There. 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay, well, I drew it correctly at least. My bad. All right, there is the standard quadratic, and we should have this in mind. This one only has 1, 0. It only reaches the x-axis and has a solution x squared equals 0 at one place. Other quadratics may not have a 0. Like this one could be x squared plus 1. And another quadratic like x squared minus 1, this one might have 2 zeros. So in general, a quadratic form can have 0, 1, or 2 roots. A factored form of a polynomial is a factored form of into linear terms of the zeros. This is fairly theoretical right now, but this is a factored form. So, for example, let's build some examples for ourselves. X minus 1 times x minus 2. What is a root? Good question. A root, also known as a 0, in this case, x equal negative 1 is a 0 or root of x squared minus 1. Also, x equals positive 1. These are the two values that I don't know exactly why we call them a root. I'm thinking of like roots, like planting a plant into the ground. Like the x-axis is like the soil, and the roots are there, and then you've got your like flowering plant above, and then your roots going below of a plant. I think of the x-axis as the ground. I don't know if that analogy helps. I don't know if that's why we call them roots. Probably not. But notice that x squared minus 1 equals 0 at x equal plus or minus 1, because proof, right? Negative 1 squared minus 1 is 1 minus 1, which is 0, and 1 squared minus 1 is 1 minus 1 is 0. Right? I think I'm like overdoing this point right now, but those are two x values that make the value, two inputs that have the function value 0, two inputs that have the output, the y value 0. Okay. So in general, an nth degree polynomial can have up to n roots, up to n zeros. We'll talk more and more about that in the future. But here I just made up an example using 1 and 2, simplest numbers. Using distributivity, right? Using distributivity, we got this. This is the expanded form. The expanded or standard form whereas this is the factored form of the same function, of the same of the same polynomial. Hey, what's up, Unix Teletype? How are you? Ooh, what makes an equation a function? Great question. Great question. I'll answer that, since if you want me to answer that later, you could say, later, could you explain what makes an equation a function? But since you're asking that, it sounds like you want to understand that before we move on. Is that correct? It's slightly a detour, but not really. What makes an equation a function? I gave a very brief intro to this, very briefly, in episode 5 with the Collatz conjecture. But I can try to give it a little more clarity here. Okay, so let's use my favorite numbers again. 1, 2, 3, 4. Every equation is a function. False. False. It is not. I can wait. I think now's I'll come back to this and give it more detail if that's what you prefer. But since you ask, I do want to treat this somewhat right now. This is a function. I'm going to give these either a check mark or an X. This is a function. This one is also a function. This one is not a function. I guess I should have used green. Isn't that much more customary? Or blue. This one is a function. This one is a function. This one is not a function. Where's my guitar music? Oh, good. Thank you for asking. Yeah, let's put the guitar music up. Thank you for asking. Patricia was asking about factoring and functions, so I just started teaching about that. But if anybody has questions about the material we've done already, I want to prioritize that and focus on that. Okay. So right now, I have 3 examples. So in fact, because this is not a function, I'm not even going to call this f of x, because that's a lie. I'm just going to say that this is a y value. All of these are a collection of 4xy pairs. But the difference is that in this one single input maps to multiple outputs. You were doing linear algebra. I was for a long time, but now this channel is focused on basic mathematics. So each x has to have one and only one value for the equation to be a function. Yes, that is exactly it. For it to be a function, every input should have exactly one output. It's okay if multiple inputs map to the same output. This is okay. This is a function. But this shape, which is more like 1, which maps to many, is not a function. This would be called a relation instead. Whereas if every x has one y, then it is a function. A function is a rule that associates a value to which associates a unique value to every point in the domain, which is the set of inputs or something. A function always has to have a domain and then a codomain. I think it's going to be best if I call it a function from A to B. I don't say range just yet. It's slightly different, but range is quite related. So we have the domain and the codomain. Most of the functions that we're used to are real numbers to real numbers, but there's many other types of functions. Am I late? No, you're not. Okay, so that's one attempt. I gave a friendlier intro in episode 5. If you want to see that, go check that out, and I teach it more like how I teach a kid. Some examples, we can think of the graph of a relation. And a a great example is the unit circle. X squared plus y squared equals 1, for example. For every x value, for most of the x values at least, there are 2 separate y values. So, let's see. Yeah, 0, 1 is in the graph, and 0, -1 is also in the collection of points that satisfies this equation, the graph of the of this relation. So this is not a function because 0 maps to both 1 and -1. In other words, one way to think of it is a vertical line test. And this might sound familiar. Vertical line test. A function must pass the vertical line test. Are all functions able to be graphed? No. That's not true. Absolutely not. Hell yeah. I'm glad that you thought that they can. That's not true. I can define lots of strange functions. Yeah, functions are weirder than you're thinking. I could have, and we do this all the freaking time in programming, we define functions of a word to another word, right? Like, maybe one example, we'll take Hunter21 and return another string H star 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 1 or something. Right? Maybe this is the function in a website that masks, that hides characters in a password or something. Or another function might also take a string and then return 1, 2, 3, 4, 5, 6, 7. Maybe it returns the number of characters, right? The count of a string. This is a function too. Like for that string, it always returns one value. And you can't graph these, right? There are other types of, there are even mathematical objects that you can't reasonably graph. But in programming, you often define a method, and they may or may not be a function. Like in coding, you can do something like let's do something like if flip coin return I don't know, return 1, else return 2 or something. like in programming, this is non-deterministic. So we would call this a method, not a function. I mean, ultimately, at the end of the day, it's deterministic if you include more state of the world and like pseudo-random generators and all sorts of complicated stuff. Like, then we're talking about determinism and but how do you define a function? Can it be any set of rules? Yeah, it really can be, as long as it's a well-defined set of rules. Like, what's a good example? You can try to think of like your reaction to a thing in the world. Like, when you come across a stoplight, here's a simple model. A stoplight can be red, yellow, or green, right? You're driving in a car, and the stoplight is either red, yellow, or green. And if the stoplight is red, then you should have the action stop, right? If the stoplight is yellow, maybe you slow down. And if the action is, or if the light is green, then you go. This isn't really a function. This almost is. This one fails to be a function because sometimes when the light is yellow, sometimes you slow down. Other times you speed up or you keep going. You want to get through that yellow light. Either slow down or speed up. Exactly. So this isn't really a function. If we wanted to turn it into a function, we need to change the domain. We're really getting off topic a bit. So I apologize if we want to get back to factoring. Like, now we need to change the way that this function is defined. Like, it doesn't matter whether you're close or far from the if your distance is close or far. If you're far away from the intersection, then you slow down. But if you're close or in the middle, probably you should say that if you're in the intersection, if you're already in the intersection, you keep going and you don't speed up, you stay at the current speed. But you see what I mean, right? Like, now I needed to change the domain, so my driving function now is not just built on the stoplight, but it's also built on the stoplight and your distance, or stoplight and position. And then we map to an action. So this is a bit more, but yeah, the short answer is vertical line test, every x has one y. Okay. Factoring, let's get back to this. How do we get from the standard to the factored form? I think the way I want to teach it to you and to others is that factoring is the distributive property in reverse. Factoring is the reverse distributive property. So first, if you get good at practicing multiple of these, x minus 2, x minus 3, here's a little worksheet. X minus 3, x minus 5, and I'm building it out of the Fibonacci numbers. Just to pick a sequence. I just came up with 4, and I'm doing them using the Fibonacci numbers. I'm just going to do it quickly. X squared once you've practiced these, you can do them in one step. Okay, so now I've made some of my own out of a sequence that we know and love, the Fibonacci numbers. Now, let's figure out how do we go in reverse. Let's jumble these up so that we don't even remember which is which. How do these... You know, pretend maybe you do it one day and then the next day you come back, you write down a randomized list of them, and how do we go back to the originals? Okay, for something like this, we want to convert it to in general, ax plus b times cx plus d. Right? We want to factor it in this fashion if we can. By the distributive property, or in other words, foiling, we know that that last term needs to be b times d. So this is a clue. This is one of our best clues. BD has to equal 2. Also, AC has to equal 1 because the leading coefficient is 1. Right? And in this, we have the middle term being ADX plus BCX, also known as AD plus BC times X. AD plus BC should equal -3. This is a general, like these are our facts, where this first one gives us the coefficient of the x squared term. This one gives us the coefficient of the constant term. And then constant term, maybe it's best to call it x to the 0. And then this other one comes from the middle term. I'm doing this in a very general way right now so that we will see how to extend it to more and more settings and understand why the patterns work. So you probably haven't learned factoring thinking about more generality like this, because I want to make sure that nothing feels magical. Like, why do the patterns work? Right? I feel so strongly that we should show the theory and like the concepts of why these things work. But now that I've done a little bit there, x squared minus 3x plus 2. We want to factor it. into two terms. Since the leading coefficients multiply to 1, I'm going to bet that both of these are 1. They're probably both 1. They don't have to be, but I'm going to assume that and see if we can make it work. They don't have to be, though. I want to really emphasize that. They're not guaranteed to both be 1. Now, the last term, these two numbers need to multiply but to 2. Well, we haven't talked about factors of a number, of prime factorization. We haven't technically talked about that yet, but you may realize that the only way for two integers to multiply to 2 would be either +1 and +2 or -1 and -2. So I could guess that they're both positive 1 and 2, maybe, and check my work and see if this is going to work. Now this would satisfy this term and this term, but it will fail this middle term. You've just seen it and been expected to know it. See, we need to learn how it works, why it works. You need to be really good at your distributivity, your foiling, before you start to try to learn factoring, because factoring is reverse distributivity. So looking at this candidate, this option, I can see that it's going to fail because the middle term will be +3 if I distribute this. And just a reminder, that's because we distribute x times this whole thing, x plus 2 plus 1 times that thing, x squared plus 2x plus x plus 2. So this one would give us +3, whereas we want -3. So you start to learn various different patterns. If the middle term is negative, whereas the last term is positive, then both of these need to be negative terms, because the signs must match since the last term is positive. The signs must both be negative or both be positive. And then I think, are there any numbers in the factorization table of 2 that add or subtract to the middle number -3? Okay, yeah, -1 and -2. And we get this one. If we try it again with something a little trickier, on this one, if it factors, again, the leading coefficient is 1, so I'm going to guess that it probably has an x term in the first components. The middle term is negative and the last term is positive, so both of them have to be subtractions. And then 40, what are the factors of 40? 40 is either 40 times 1, 20 times 2, anything else? Yes. 4, oh wait, here. When I do factorization, I prefer to think we want two numbers that multiply this number times this number, they should multiply to 40, to positive 40. So, can we divide 40 by 2? Yes. Can we divide it by 3? No. Can we divide it by 4? Yes. Can we divide it by 5? Yes. Can we divide it by 6 evenly? No. Can we divide it by 7 evenly? No. 8, now we have started repeating, so we're done. This is the entire factorization table for 40. 40 equals any of these pairs of numbers multiplied. Now, do any of those, do I see a way to combine and add or subtract to 13? Do any combination of these add or subtract to 13? Yes, the last one, right? 8 plus 5 is 13. So we could make this one -5 and this other one -8, maybe. Double checking. Double checking that this factorization worked. Hey, big news. Yo, that's awesome. What was your hackathon? What was your hackathon project? That's really exciting, Avi. Happy to hear that, dude. Very happy to hear that for you. I hope that helped a little bit. Let's do another example. If this factors, it probably has an x as the first term of both. Both of them are going to be negative because the middle term is negative, but the last term is positive. We want numbers that multiply to 15 and add to 8. 3 and 5. Yeah, congratulations, Abhinav. That's really freaking awesome. So I draw the little factored parentheses, and then it's like a little puzzle to try to find numbers that multiply to the last number and add to the middle number. 2 and 3 in this case. Let's make up a couple more problems. I want something tough. I'm going to make something tougher. Undo. Find n such that x squared, let's keep things, plus nx plus 123 factors. Let's find some number so that we can factor this. This is going to force us to think a little bit more about how do we do this process. Okay, well, what is the simplest combination of numbers that multiply to 123? It would be 1 and 123. We could subtract both of them or add both of them. Are there any other factors of 123? Are there any other factors of 123? We will learn. I know it very quickly that 3 divides this, because 3 divides 1 plus 2 plus 3. What is the 1 plus 2 plus 3 is 6. And 6 is 2 times 3. So that's a pretty amazing fact that not everybody knows or has ever learned. But I know for a fact that 3 will divide 123. 3 divides 12 4 times. And 3 divides 3 1 time. So 123 is 3 times 41. So we also could have x plus 3 times x plus 41. Or we could have x minus 3 times x minus 41. Right? 41 is prime, so I think that's good for us. Anything else? I think that those are going to be all of the possibilities. Again, yeah, because 41 factors as 3 times 41, and 123 factors as 3 and 41, and 41 does not have any factors other than any non-trivial factors. So these are all of the options for how we could factor this quadratic. So I could say find all integers n such that this factors. This first one, when we distribute, it would be x squared plus 124x plus 123. So our final solution is, let's collect these numbers. This next one is going to be the same, but it's going to be minus 124x plus 123. This next option would be x squared plus 44x plus 123. And then this last option is x squared minus 44x plus 123. So given any of these for standard polynomials, you could factor them thinking of the factorization table of the number 123. So these are all of the possible middle coefficients. Wow, there's a reasoning to this other than fairy dust and magic. Yeah, we all learn it as fairy dust and magic, and it turns out that there's a better way. There's actually theory behind this stuff. Like, I don't remember anybody when I was growing up. I don't remember anybody teaching or emphasizing that foiling is double distributivity. That it's just the distributive property twice. Foiling, like I don't know if I've ever done this explicitly in the series yet. And I don't think Lang has this exercise. This as an exercise. But this is, by distributive property, A times this entire number plus B times that same number. And now we distribute from the right, AC plus AD, BC plus BD, and now we just did FOIL. AC plus AD, BC plus BD. Like, we just memorize this as FOIL, as like a special mnemonic rule, but all we're doing is just saving one step. We're just skipping this one line. Like, we're just saving one line of paper. But in the process, we need to trust that this process works, and we just believe it on just as faith that foiling works, and I don't understand why. But we're only skipping one line. We're not, like, is it really worth taking this as an assumption that foiling works when the alternative is to learn distributivity and then just do double distributivity? And now there's no fairy dust, there's no magic in it. Like, it's clear, it's simple, it makes sense. Now, it's like one less thing that we just have to memorize and trust, which is a huge thing in math. Like, we don't want to just believe and memorize and trust that patterns will work. The whole point is to try to understand why the patterns work. That is what math really is. And so I don't remember somebody teaching foiling as double distributivity. Right? And then factoring is also just distributivity too. Factoring is also just distributivity, but in reverse. We have something that is expanded and we want to factor it if we can. Now, sometimes you can't. I mentioned that x squared plus 1 does not have any zeros. It does not ever reach the x-axis. We cannot factor this as x plus a times x plus b for anything, because we would need a times b equals positive 1 and a plus b to equal 0. The factorization table of 1 is either 1 times 1 or 1 times negative 1 times negative 1. These are our two options. The first one, x plus 1 times x plus 1, is x squared plus 2x plus 1. The second option, x minus 1 times x minus 1, is x squared minus 2x plus 1. So this we cannot factor. So that's where there's something more difficult about going in reverse. Sometimes you can factor, other times you can't factor. There's another twist to this whole story, that this thing does factor if you invent a factorization in the complex numbers, but we will talk about that in the future. But this is imaginary numbers, and you can imagine that there is a solution, in which case this does factor, and it turns out that that makes a lot of math really nice. Like, introducing complex numbers creates a really simpler, more beautiful, easier number system to work with. But in the real numbers, we don't have a factorization of this polynomial. Cool. Any last questions, y'all? I think we've been going for a bit more than I was planning. I had fun today. I hope that this helped a bit. So, Patricia, seriously, if you want to try to practice some factoring, pick your favorite sequence. On day 1, make a bunch of distributivity problems for yourself. Create a table of 10 of them. Maybe flip coins so that sometimes, I don't know, maybe the first table, they're all additions. Or some of them, they're all additions. Some of them, addition, and then a negative, then a negative, and an addition, and then 2 negatives, right? Mix them up. For now, it's best to just assume that the first term is always x. But you can make that more complicated later. And then again, pick your favorite sequence. I keep coming back to sequences because they're so useful. Like, a lot of people are going to like digits of pi, prime numbers, Fibonacci numbers, just the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and fill out this table. So maybe prime numbers. How many primes do I remember? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 30, oh wait, no, 39 is not prime. 41, 43, 47, I think. Yeah, 47. 51 is not prime. That one is a trick. That one will catch you. So I just made up a bunch of little problems for myself. And some of these are going to get hard. I noticed that some of these are going to get hard. But you can make up your own problems. And then, like, here's one way. Then do that on day 1. Somehow pick a way to shuffle them. Shuffle and right on page for day 2. Like after you find the expanded form, then go from expanded back to factored from the problems that you made up for yourself. Now factoring makes some sense. Thank you. Now I practice. Heck yeah. That's the attitude. Now we practice. Now we all practice. Okay. Oh, what did you do with 123 to know it was divisible? This will be one of my videos in season 2. One of the coolest facts is, hey, Nizam, what's up, man? Good to see you. It's going well. We're almost done with this. I wanted to only do an hour, but we're in super overtime right now. 3 divides a number if and only if 3 divides the sum of the digits of that number. For example, 3 divides 123. It also divides 120 or 12,345. I know that in a second because 1 plus 2 is 3. 3 is 3. 4 plus 5 is 9. So 12 is divisible by 3, 3 is divisible by 3, 45 or 9 is divisible by 3. 3 divides that number because 3 divides 1 plus 2 plus 3 plus 4 plus 5. Let's double check that. That's true if and only if 3 divides 1 plus 2. Oh, hey, triangle numbers again, right? Triangle numbers. 1, 3, 6, 10, 15. That's true. 3 does divide 15. Tomorrow it's a Chris session, but you're welcome to join, Nizam. Yeah, you're like a long-standing member, of this group. You have lifetime license. You can keep showing up to the Zoom forever. I think tomorrow, yes, we do have a masterclass with Chris, and I believe tomorrow we have Ashley signed up. Yeah, Ashley is signed up to be the student tomorrow. Should be fun, dude. Should be fun. Hope to see you there. 1, 2, 3, 4, 5. It also divides 1, 2, 3, 4, 5, 6. It also divides 1, 2, 3, 4, 5, 6, 7, 8. Because 7 plus 8 is 15. So I think that this is an amazing one. I know for a fact already. 1, 2, 3, 4, 5, 6, 7, 8. This is a huge... And 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Because 9 is also divisible by 3. 3 divides 12 4 times. 3 divides 3 1 time. Divides 4 1 time. 15 5 times. 6 twice. 7 once. Twice. Carry the 8. 3 divides 18 6 times. And 3 divides 9 3 times. It's amazing, right? Isn't that really cool? I just made that up as a little practice problem. Like, show that 3 divides this number. When's the next one? 8, 9, 10. It does not. it does divide it divides this number as well. It also divides this number. Does not divide this. What about this? Now I'm just having fun. It does divide this, right? 1 plus 3 is 4, 8, 9. Yeah. So it divides that number as well. Isn't it cool? Isn't it cool? I wonder why is that though? Ah, good question. I think we can prove it by induction. I think you could prove it by induction. I haven't learned the proof of this one in a long time. Yeah, take care, Nizam. By the way, Nizam, if you want to help me out, if you want to support what I'm doing, all of the stuff that I'm doing, watch this video, everybody. This is a brand new video from yesterday. This one is meant to be for everybody, even if you hate math, even if you really don't like math. There's no real math in this video. I'm just talking. I'm just like talking to the camera. Yeah, it would help me out, y'all. And I think it's a good video, personally. Cool. All right, thank you everybody for watching. I had fun today. Yeah, thanks for being here. Thanks for your questions. Today we worked on factoring primarily. We talked a bit about the definition of a function. We also gave a sneak peek to season 2, and one of my first videos will be about deliberately practicing addition and multiplication. Many thanks. Yeah, you too. Thank you for being here, Patricia. It's always great to see you in the chat. All right, bye everyone. I had fun today. My iPad is running out of batteries. All right, bye.